So what hopefully you've noticed is that our focus has been with different two new functions as far as what we've been focusing on with exponential and logarithmic functions. It's definitely important that we're reviewing some of those things. As we saw on Monday, definitely want to make sure you're comfortable with your properties of logarithms. Okay, so dealing with, like, say, the product property, power properties, and especially those inverse properties when it comes to logarithms. Here's a good example of an application problem that we can look at. And we're going to look at some other application problems because our next step then is to look at growth and decay models when it comes to dealing with different perspectives, whether it be business. As we see here, I have an advertising one. We're going to look at some other ones that may not be business, but it could be something like population growth, right? So population growth would be another good example where these models are helpful. Okay. Now, for this particular function here, we're focusing on a logarithmic function. It's always important that no matter what we're doing, always remember, just go back to those foundational things. Highlight the function you're working with. Going to tell us a lot of what we're dealing with moving forward. Okay. One thing I would point out here, because you're dealing with a logarithmic function, the image that you want to have in your head from a graphing perspective test 1, 2. All right, sorry. So the image from a graphing perspective here that we should have is a vertical asymptote with a graph that looks like such. So that was something I did just kind of quickly yesterday, just showing you from the inverse perspective. We took an exponential and we inverted it to get to here. All right. But those are some of the reasons we want to just kind of have an idea of what to expect. So know, like, our domain is going to be limited here. When we see this, it says A has to be greater than or equal to 1. Well, technically A had to be greater than 0 to start with. They just limited it a little bit more. So what they're saying is start about right here and then go, and don't worry about all this other stuff. Okay. Keep that in mind. With that said, this is what's telling us stuff about our function. Make sure you're highlighting things as you work through stuff. I know we've looked at some other application problems, but like, as we look at this, our function is going to represent the number of units sold. It's why they probably use the letter N to represent that. Okay. The A here is going to represent the amount of money spent on advertising. Okay. So make sure you're highlighting that, and also make a note here, it's in thousands of dollars. So if, like, you get A equal to 5, what we're thinking there is $5,000. All right. Any questions or concerns there before we jump into what it's asking us to find and such? All right. So then we'll see your part A then is going to jump in and says, hey, let's find out how many units were sold after spending $1,000 on advertising. Okay. So with that said, do we want to use the function we're given, or do we need a derivative right now? All right, this is going to be our given function, right? Just go plug in something and let's find it out. With that said, what should we be using for our A value on this first part? All right, but so A equals what? All right, be careful here again. Go back to the fact that it's in $1,000, right? So, hey, this would just be 1. So, like, if I said, hey, we're going to go focus on $2,500, then A would be 2.5, 2.5. Okay, so be careful to always check your problems when you're dealing with stuff like that. So here, we want to make sure to go and say, hey, what is N of 1? All right. That's going to equal $2,000. Okay. The reason that is the natural log of 1 equals what? 0. Okay. Excuse me. The log base any value of 1 will always be 0. And the connection to that, if we take kind of an inverse perspective, is we're saying like, hey, e to the 0, what does that equal? Well, hey, anything to the 0 exponent is 1. Okay. So anytime you have a logarithm with an argument of 1, it equals 0. So hey, 500 times 0 is gone. That means if you do $1,000 of advertising, how many units are going to be sold? Everyone follow and agree with that? Any questions or concerns? All right. So the next thing then it goes on to say, hey, let's go find n prime of a and then n prime of 10. Okay. So what function is that wanting us to find again? This is where our derivative function comes in, okay? Making sure we see the difference in notation. It's still the same function as far as n is concerned, right? We're using that as the foundation, but what we want to do now is to say, hey, we're going to go from here to its derivative. Make sure you see here, though, the input variable is a, so you wouldn't want to use d dx here. We want to use d dA. Now, with that said, what's the derivative of constant value like 2,000? All right. Well, I'll go with that. What do we do with the natural log? That 500 times the natural log of a. 500 over a, and if you need to, write it separately, of course, right? But know that at some point, we're just going to write it as 500 over a. And you'll find with this particular problem, you definitely want to simplify because that's going to make it easier to work with as we move forward, okay? But this goes back to what we talked about on Monday, that, hey, when I look at a logarithm, and especially like a natural log, the derivative of that is going to be 1 over whatever's the argument, okay? And the chain rule here would just give us times 1, so we don't need that in this case. Any concerns with that, the derivative of natural logs? All right. With that said, then moving to the next step, it said not just to find the derivative, but go plug in 10. Now, what does a equal 10 represent again? All right, this is us spending $10,000 on advertising, okay? So make sure we're keeping that in mind as we're going through this. One of the things you'll find here that's like making adjustments like this might make the function a little bit easier to work with. Sometimes it's a visualization approach. Like if you're trying to build a graph on something by using this in thousands of dollars, you center it a little bit closer to the origin, which will make it easier to read and interpret. Okay, so there's a lot of different reasons you might want to do that. And we're going to kind of briefly look at the graph here in a second. But just be careful now that we're with the derivative. It's not going to be the amount of number of units sold, but the rate at which it is changing, right? So what is the rate at which the number of units is being sold is changing when $10,000 is spent? Hopefully what you'll see here is that's not too bad to deal with because we're just doing 500 over 10, which gives us 50. Now, from that, though, the main thing that we could say is the rate increasing or decreasing the more you spend when we're looking at $10,000?
Increasing.
It's increasing, right? So, different ways we could look at that. It's like, hey, if we spend $10,000, that's helping us boost our sales by 50 units, right? Other things we're going to look at too is moving forward as we deal with the different applications, we're going to get to words like marginal, right? So we're saying like, hey, if I look at this from the perspective of I'm spending 10,000 on advertising, what would happen if I spend 11,000 on advertising? It's going to increase, and right, we can expect that it might be about 50 more. Okay, if I can go find how many are being sold when we spend $10,000, I should expect 50 more units possibly, right? That's just an estimate, of course. Okay, so it's not the exact graph because we're using the derivative to help look forward. Any questions or concerns with that, though? All right. Now, as far as the next part, it's asking us to find maximum and minimum values. Okay, so we've kind of talked about this a little bit. One of the main things I would definitely connect it to, this is where horizontal tangents are very helpful for us. Okay, if you think about a graph like this, right, this would bring us back to a quadratic. The horizontal tangent occurs down here at the bottom of my graph. Right, we call that the vertex of a quadratic, and if you remember from college algebra, some of the things we talked about, hey, that's going to be the minimum or maximum of a quadratic. Well, from a calculus perspective, hey, that's a horizontal tangent. Anywhere I have a horizontal tangent, I possibly will have a minimum or maximum value. Okay. Now we're going to go in more detail with this as we move forward in our course. Right now, we're going to focus on the logarithmic and exponential functions and bring in some more applications. Okay. But let's look at the graph, just kind of looking for those turning points. Okay. That's our whole focus here. So let's look at the graph real quick and consider the possible turning points. Now, what I'm gonna do is just a quick little sketch, of course, okay? So make sure you see at the bottom, I'm counting by twos here. Whereas over here, I'm counting by thousands. Follow me on that? I want to do that though, so that way when I go plot my first point for this graph, I can put it right here. Just to make it as straightforward as possible. Now, this other point I'm plugging in, since our derivative focused on 10, I went plug 10 into our function. So what you're going to see here, this is going to be 10, and it came out to 3,151 approximately. I'm rounding, of course, to get to that. Not going to be the best thing to graph by hand, right? Having a visual graph will help. But just make sure you see here, when I do this graph, it's going to look something like this. Okay. Why am I not worried about this piece here? What did I say that's going on up here that said, hey, don't worry about anything past one? And I messed that up, y'all. But why are we not worried about, like, say, a half, spending $500? The domain is restricted, right? First and foremost, anytime you see natural log, as mentioned, hey, I only want positive numbers, no zero, nothing. But remember here, that's an important piece here. I'm going to start at this value, which we already found. That was what this first part focused on. Okay, so if we go back to here, make sure you see that's where I'm getting this point from. Okay, so make sure we're taking the information out. If they didn't tell me to find that, it would have been a good idea to plug in A equals to 1 to just start anyways, so that we get that first point in place. Now, with that said, though, this graph is going to continue to increase the further we go out. Okay, it just does it really, really slow. Okay, but it will always increase. There is no horizontal asymptote to say that there's something that's going to stop that. For a logarithm, as mentioned, it has a vertical asymptote. Okay. With that said, then where would we look to even get a minimum or maximum value then? Are there any places that this graph will turn and start decreasing? If it's always increasing here, will it ever start decreasing, as I just mentioned? We have the derivative to help us, right? If I'm never plugging in a negative number here, 500 divided by any positive number means my result will always be positive. Okay. And of course, the bigger your number gets, the smaller and smaller that is, right? So think about if you plug in 100, right? If we say, hey, let's spend $100,000 into advertising, well, that's going to be 500 divided by 100, which is 5. As you get to something like, say, $1 million, now you got to really look at that to perspective. That's 500 over 1,000. So your derivative is only going to be a half, right? So those are ways that we can interpret that. But no matter what I plug in here, this is always going to be greater than 0. So we wouldn't have a horizontal, anywhere along this, we will not have a horizontal tangent, sorry. So technically speaking, we don't necessarily have any minimum or maximums. However, what's special about this point? When you consider this point and knowing that it's only going to go higher beyond this, what would you say about it?
Wouldn't that be the minimum if, since our restriction is A is greater to or equal than 1?
That would be the idea there, is that we're dealing with it being the lowest point, right? So what I want you to see here is that we'll go into more details of minimum and maximums, right? As far as dealing with horizontal asymptotes, but make sure you understand that, like, hey, this is actually going to be our minimum value. Okay. Now I just did a quick sketch by hand using a calculator of some sort. You can definitely get a better graph. For some reason, it doesn't want to help me get a graph right now. Oh well, deal with it later. Now, the one thing I will point out though is the next part here where it's saying what is the limit as a goes to infinity of our derivative. It's 0, right? So remember, that's one of those limits to infinity that we talked about. Hey, it's 1 over a, could be 500 over a, right? It's going to approach 0. It's going to get so small that it's not distinguishable between the value and 0 itself, okay? But as I was just mentioning, it's always going to be positive when we plug a value into our derivative, but it's just going to get smaller and smaller and smaller as time goes on, okay? So with that said, their question is, does it make sense to continue spending more and more money on advertising? Or is there a point where you would consider that, hey, we've spent enough?
The more they spend, the more they have, the more revenue they have.
Okay, so if they spend $1 million on here, will it be as efficient as spending $10,000? So if I do n prime of 1,000, all right, and we compare that to here, remember, as I mentioned, that's actually only going to equal a half. So is it worth it to spend it, just get a half a unit sold? Right? The idea there is we have to consider the fact I can keep spending as much as I want, but at some point it's not going to make a difference at all, right? The value will be so small, it doesn't help you. Okay, like from a business standpoint, I would even say, even when you get here, when you're considering all it's going to help me with is a half a unit, well, let's make sure we consider how much one unit cost, right? We would definitely need to go look into the cost of production, how much we're selling for. Those things would definitely need to be a part of that perspective. Okay, but hopefully what you'll see here is I definitely don't want to just keep spending money on advertising without considering when it becomes so insignificant of a difference. Okay. Now that's using their model, of course. That's not going to be every situation, right? This company that's building consumers' responses to whatever they're making found that this logarithmic function, sorry, fit what they were working with. That may not be true for everything, right? You might have some other stuff where it might benefit you differently, okay? Any questions or concerns here with this first one? Are we good with what the A value represents and how we had to interpret that? That was one of the things I wanted to make sure to point out. Just always watch that because it sneaks in sometimes. All right, we're good with the derivative function. Getting here. All right, and as I mentioned, I just did a quick sketch here, just kind of give us a visualization of it, all right? Not every problem is going to ask for a graph, but sometimes looking at the graph helps you kind of see what's going on, okay? So that's why I wanted to add it. Now, as we move forward, we're going to have different types of application problems to deal with. The good news is some of this kind of connects to what you learned in college algebra, so it's not completely different. However, we're going to bring in the perspectives we've been discussing with derivatives in our calculus course here. Okay, so this first one here, you'll see it's going to focus on exponential growth, and we can also move on to decay at some point. All right. What you'll see here, though, is they give you this instead. They're going to start by saying, hey, here's the derivative of a function. Make sure you see here, though, the way that they say this is like the derivative of a function with respect to x equals some value, some constant multiple times the same function. Okay. Now, for us, examples of this. Here's a function that we should be familiar with, right? Compound interest, where it's compounding continuously. Another way to write this, instead of just a, you can say a of t to bring in function notation. Okay. Now, with that said, let's just focus on the e to the RT aspect. What is the derivative with respect to t of e to the RT? Just so you can kind of understand where they're coming from, where our book presents this in. Well, first and foremost, remember that, hey, the derivative of an exponential function, I'm just going to copy the exponential function. But here becomes the important part. What do we need to multiply with now? Right? This is where the derivative with respect to t of that exponent comes in. So this is going to be r e to the RT, which is where that k value comes into play. Now, what you'll see, if you start with the derivative and then you go forward, you'll have your interest rate for something that has to do with compound interest, right? The rate of growth or decay will be given to you from the beginning. You won't always know the initial amount. So we'll always have to have a little bit more information to know that, okay? So you'll see they use the letter C there on that second part just to kind of highlight like, hey, the first part, the K is meaningful, which hopefully you'll see here, the K is meaningful because if it was a compound interest situation, that is my interest rate, okay? As you go forward, you'll see here with that theorem 9, they use the similar letters here where they call the K the growth rate. So make sure you just see there like, hey, that's going to be the rate. It's going to be a percentage that we're focusing on. So we're going to expect decimal values back from that and so on. Now, with that said, one of the things that we will talk about with this is definitely going to be growth rate and such. You'll see here they have the doubling time. And I thought this was kind of a significant one because as you deal with this, what they're doing is they're saying that like, hey, when I consider any situation that has unlimited growth to it, uninhibited growth as the book calls it, right? I can calculate the doubling time using this idea of the natural log of 2. Well, where does that come from? Well, if you think about this, y equals 2 to some exponent, right? That's where it's based off of this idea that, hey, doubling is thinking of powers of 2, right? So if you put money in a savings account that has a growth rate of $1,000, how long would it take to double? Okay, that would be a question that we can remember. So if we take that perspective and we assume that this grows continuously, we would say, I want to know when it gets to 2,000. I have no clue what percentage I just said. We'll use 8%. Right? And I'm just making up a general situation to show you where this comes from. Well, what's 2,000 divided by 1,000? There's where your 2 comes from. Okay. Now, as far as solving this comes in, if you have it in this exponential perspective here, using that formula, this is where the natural log comes in. We have to do the natural log of both sides to be able to get to what we're looking for. All right. And what you'll see here is this is where the natural log of 2 equal to that 0.08 times t, the time that we're dealing with, comes into play. All right. Now, the big difference here is they use a uppercase T because the focus of this was doubling time. Right? Because we're using natural log of 2, the specific use here is doubling time. Okay. Well, they have this thing that they call the rule of 70, which is definitely helpful, like from a business perspective, when you're talking about investments. I know at one point I was looking to sell insurance for a local company here, and during their meetings, this was definitely something that they brought up, like, hey, make sure you keep in mind when you're talking to others about your product that this has an impact on what's going on. The rule of 70, right? Well, where did they get this from? Well, remember, interest rates or growth rates are going to be percentages, right? If you just do a quick multiplication here of 100 over 100, this becomes about 70% all over 100 times whatever your rate is. No, sorry, that's backwards. What am I trying to write? Sorry, the doubling time is what I'm trying to say. If you take this right here, this will give you how long it'll take for something to double, right? Using this situation, you say, hey, this is about 100 times that 0.69 all over 100 times whatever your rate is. Okay, the natural log of 2 is where the 0.69 is coming from. So the rule 70 is saying, hey, take 70 and divide it by whatever your percentage is of growth. So like if we take that problem I just made up, 8%, do 70 divided by 8, and it will tell you how long it takes to double. Okay. Which if you would have looked back at it, I had previously the natural log of 2 equals 0.08 t. All we could do there is divide both sides by 0.08. The whole 100 thing is just making it whole numbers rather than using decimals. That's the big difference.
So, the rule of 70 is just a way to make it easy.
It's just a way to, hey, how can I get kind of a quick, it's not going to be exact, right? Because it's an approximation, but a quick, how long will it take stuff to double? Right. So if you have an account that you're looking to invest money in, and let's say it has a 11% instead of 8%. Well, we can say, hey, the time it takes to double, I'll just do 70 divided by 11. And that's going to be whatever time that interest is working. Approximately, right? So if it's continuous interest, hey, it's going to be the number of years to take doubling, right? Now, keep in mind, that can be used for saving situations, but it also can be used for stuff if you have a loan, right? We have to make sure to keep that in mind as we think about interest. Like if you're using credit cards, stuff can hurt you pretty quickly, right? With a credit card. If you don't pay attention to that, credit cards have like 25% interest on them. If I take that perspective, how long, if it's doing a monthly thing, if it compounds monthly, right, at 25%, how many months does it take for that debt to double? Not even 3. Right. So those are things that we have to be careful of. Now that I'm just making that up, of course. Don't make sure you read the terms and conditions of stuff like that. Of course. But that to me is an interesting perspective to make sure and understand, like, why would we even want to jump into this? Well, when it starts to deal with money, like loans, if you have savings or investments, these will definitely be stuff that we look at. Okay. We're also going to look at some other examples, but the first one is what we call uninhibited growth. Okay. So what happens if something can just keep on growing and there's nothing to stop it? Okay. We will also talk about limited growth as time permits today. But here's a problem if you want to just take a picture of it so you don't have to copy the whole thing down. But what you'll see here is this is an example of just someone bought a comic book back in, what do they say, 1939? And recently, as far as 2010, it was sold at auction. The original comic book was purchased for 10 cents, but it sold for over $1 million in 2010. Okay, so we're going to use an exponential model to say, hey, how has this price of this comic changed over the years? With that said, we're assuming that it's just going to continue to grow in value. This item will just continue to grow in value. Now, what you'll see here is they give us this model to remind us, okay? But if it says this, we should be thinking this right away. If it says it has grown exponentially, I should be thinking dV dt equals kV. All right. Now, with that said, whenever we're getting here and it asks us to find the function, as we see here in part A, the one thing that we have to understand that once it says it's growing exponentially, we're thinking that V equals CE to the KT. Right off the bat, that's what I'm thinking. Now, it gave me the rate of change here, okay, because we can approximate the rate of change. But make sure you see that was the reason I made sure to show this here, that like, hey, we can connect this back to those exponential growth models that we used in college algebra. You know, my brain just went blank on this. Oh, everything I looked at and worked out right before I came in is gone right now, y'all. Sorry. All right. Okay. My brain was not going to do that. I'm glad I. Give me a second, y'all. Hello. All right, I'm back. Sorry about that. The main thing that you need to see here is we weren't given anything as far as information is concerned. We were just given 2 points of perspective as far as the data is concerned. Okay. So with that said, if you know something's growing exponentially, we can use those 2 points of data, plugging them into the exponential side to find the other side. Okay. The rate of growth is what I'm trying to say there. So if we use this V of T thing equal to CE to the KT, all right, some things that we do know. First and foremost, we're using this as our initial value. Because that's our initial value, that helps us with this piece here. All right. anytime you deal with an exponential function, if we just go plug in 0 here, so if we look at v, why is it doing that? V of 0, it'd be CE to the k times 0. Well, hey, that whole thing equals 1. So all you're left with is your C value. So the C value represents the initial amount. So one thing we can say about our function then is that, hey, V of t equals 0.1 e to the kt. Everyone good with where that's coming from? Now, what we really want though is our rate of growth. Okay, the rate of growth, to get that, well, we have another point to plug in. If we plug in this other value that we're given, what happened in 2010, that's where this piece comes from. Right, so if you did 2010 minus 1939, that's where the 71's from. Okay, what they're saying is that, hey, V of 71, which equals this 1 million. Make sure I'm not missing anything. 75,000 right here equals 0.1 e to the k times 71. Once we plug in both those points into our function using the initial value that we were given and this second point of reference in 2010, the only variable that's left here then is going to be our k value. Which is the exact thing we wanted to find anyways. Okay. Any questions or concerns with that? All right, so to solve this, first we need to multiply both sides by 10. All right, and as I showed kind of quickly before, in order to solve this exponential, we're just going to use the natural log on both sides. What you'll find here, the most straightforward is, since this is just e to some power, you could go ahead and just write it as the natural log of that value. And at that point, we'll have our k value, k being approximately dividing both sides by 71. Sorry, I should have stated that. No, I'm just rounding this, but hopefully what you'll see there is we were able to find this. The one thing we do want to remember, this is a decimal, right? But how could we write that as a percentage too? So make sure you're keeping both perspectives in mind, like, hey, this is 22.8%. For the math side, we'll use the decimal. But as you solve like reference points, right, you need to make sure you go between the percentages. Now, with that said, though, this means we can go update our model. That V of t then equals 0.1 e to the 0.228 t. That'll be what we use moving forward. If you want to be more specific, you can keep this value here. This is the exact value. All right, but we should be good as far as approximations with the 22.8%. Okay. What I'll say there is just make sure you always double check like what it's wanting from a rounding perspective on a problem. I don't think it said anything here. Is everyone good though where I'm getting that from? Are you good with where I got the 0.1 from?
Yes.
Are you good with why I plugged these in here? Oops. plug this in here and here. Okay, so make sure you understand that in order to solve this equation, we have to take the natural log of both sides. That's where this is coming from. But the
71 is the number of the years, right?
no 71, yeah, the number of years from the initial amount, right? Because we're looking at 1939 to 2010. Okay, so I plugged in that, but whenever you do this natural log here, it just equals the exponent, 71K. Is it what you typed into your calculator? Did you put parentheses at the end of your natural log? Do you have the 4 zeros at the end? Okay.
Whenever my like by 10.
Yeah, so whenever we were doing this, we had to multiply both sides by 10 up here, right? So I did times 10 here, times 10, so that we can get rid of that piece there. Okay. I kind of skipped over that step, sorry. Now, with that said, then, the next step wanted us to go approximate the value in 2020. Well, that's 10 years later, right? So that'd be like saying, hey, V of 81. Okay. So we want to take this very thing that we found and just plug in 81. Now, the key word there was a approximate, right? So we're not necessarily looking at, I need an exact perfect match here as far as that's, I think that's where like, hey, 22.8% is a pretty good representation of what we're working with. Okay, so we want to go to our calculator again. Instead of T though, remember we're putting 81. Now, is it going to be a tremendous difference from this? Okay, that's going to be an interesting thing that we want to look at. Well, this is where like that doubling time would be helpful. Okay, so T equals 70 divided by 22.8. I get 3.07.
We will follow the same steps. We gotta change the T from 71.
To 81. Yeah, and plug in 81. Yep. But we don't know what it is this time. We're plugging in to find out. But with that said, the doubling time, if I just do that quick rule of 70, right? 70 divided by 22.8, we get 3.07, which means what? How long does it take the value to double? Years, right? Our whole focus, as mentioned, our whole problem's built around years, right? So what we would say, hey, this takes about 3 years to double. So in 10 years, we should expect this to double probably 3 times, right? Now that's just a quick estimate. When we go plug this in, our value that we find is end up going to be $10,484,566. Right? So if you double 1, it goes to 2 million. Double 2 goes to 4. Double it again, it goes to 8. So that's pretty close to what we were expecting for it to double at least 3 times. Okay. Any questions or concerns how I got to the function? They wanted me to look at 2020. Right. So I just did the idea, hey, that's 10 more years from 2010. So I just took 71 out of 10 to it. Okay. With that said, though, the other problems wanted us to find the doubling time. Well, I kind of did that already. Sorry. I did it out of order. What makes sure you see here, as far as this doubling time was concerned, that's where I just did a quick kind of rule 70. You do the natural log of 2 all over the 22.8. Sorry, not 22, 0.228. If I use that instead of 70, guess what I get? Is that any different than what I said over here? Just a slight amount, right? This would be one thing, just kind of share with me what the computer does, right? If you're on Pearson, to me, the rule of 70 should still be practical here, but to be safe, I would just use the natural log of 2 divided by your percentage in decimal form. Okay, that will definitely be, because even here I'm rounding, right? But 3.04 is a little less than 3.07, so Now, as far as the last one is concerned, it just wants you to take the function that said equal to 30 million. Okay, so we'll save that for later though, okay? But some of the other things that we will need to talk about is like, look at the graph real quick, so, but we'll save that for Friday. And I apologize for my blank moment that happens to me from time to time. Thankfully, it's only been once this semester.
This kind of math, I haven't landed.
We believe it's my sinuses and allergy. And like I said, my brain just shuts off for moments.
That happens, yeah.
So,
And I think,
mhm.